Welcome to NeurOn Air, the official podcast of Neurotech U of T, where we bring you the latest breakthroughs in neurotechnology straight from the experts. From groundbreaking researchers and cutting-edge engineers to pioneering clinicians and bold startup founders, we explore the innovations shaping the future of neurotech.
We are on a quest to spark curiosity, fuel conversations, and inspire the next generation of neuroprofessionals. Whether you're a student, a tech enthusiast, or just neurocurious, you're in the right place. In this episode, we welcome Dr. Brokoslaw Laschowski, a renowned computational neuroscientist. He is a research scientist and principal investigator at the Toronto Rehabilitation Institute and an assistant professor at the University of Toronto. Dr. Laschowski also directs the Computational Neuroscience Lab, which explores the intersection of neuroscience, cognitive science, and artificial intelligence. His award-winning research has been published in leading journals like Frontiers in Neurobotics and featured by media outlets such as BBC, CBC, Forbes, and Science Magazine.
Hello everyone, welcome to the second episode of NeurOn Air. Today our guest is Dr. Laschowski, and thank you so much for joining us today.
Thank you for having me.
Right, so let's get started with our first question. You work at the intersection of neuroscience and artificial intelligence. So for our listeners who may not be familiar with your work, could you briefly describe your background as well as what motivated you to pursue a career in computational neuroscience?
Yeah, so I think I've kind of always been really interested in concepts like the mind, and now we do a lot of work in artificial intelligence inspired by that. But before I got involved in AI, my background is actually in neuroscience, kind of like yourselves. But at least at the time that I did my undergrad, which it sounds like maybe it's changing these days, there wasn't really a neuroscience program here at the University of Toronto. And so before I kind of got involved in some of that, my very first year here at U of T was actually in the General Arts and Sciences program. And there I was taking courses in psychology and philosophy, again, interested in the mind and how it works. And I remember it was probably around this time, like April time, when we were doing our finals, and my mom visited me here in Toronto, and she's like, oh, how things are coming along, like how's exams and those kind of stuff. And she could tell I was very stressed, and she was like, what's wrong? And this is literally what I said. I was like it's hard for me to be motivated to study for my courses when I don't even know if I exist, and so she thought he's really having some kind of existential crisis. And so I ended up then transferring that a few months later. And like I said, there was no neuroscience program here at U of T at the time. And so I ended up rolling in the kinesiology program. And it was there that I took courses in neuroanatomy and neurophysiology and human motor control, sensory motor integration, stuff like that. And then after my undergrad, I ended up doing a master's again in kinesiology, again focusing on neuroscience. And then I made the official switch into engineering. I thought, I really like neuroscience. I really like how does kind of the mind come from the brain, but I want to understand it more from a quantitative perspective. So I got involved in engineering, did a master's, and it was then, we can talk about this later, when I started applying mathematical modeling to understand how does the brain work and how does it kind of give rise to complex behavior, specifically motor control. And then kind of building on my master's, looking at kind of computational motor control, I ended up doing a PhD again in engineering. This was all at Waterloo. And there we went from kind of extending modeling work for the motor system to then sensory system. So a big part of my PhD was then kind of in this area of deep learning for visual intelligence. So trying to be able to mathematically model the visual information processing neural networks in the brain. And then after I finished my PhD, I did a postdoc here in Toronto, and now I'm the director of my own computational neuroscience lab.
Well, that's quite the journey, and it's quite inspiring as well. I guess for us too, right? Like, we kind of have this liberal arts education in our first year, and then we kind of move into whatever program that we feel like we want to pursue.
So you told me before we started that you're in computer science, but then also neuroscience as well.
Exactly.
So is your home department the Department of Computer Science?
No, actually, I'm out of stream for computer science. I started off as part of the life sciences program.
Okay.
So, yeah.
Okay. And yourself, what's your home department, I guess?
I guess arts and science.
Okay. Yeah.
Both business and cognitive science are within arts and science. So yeah.
Okay.
It's funny you speak about exam season because we're in the middle of it right now.
Yeah.
And we would relate to you more than anything. The existential crisis, the stress.
Yeah. How's it coming along, by the way?
Going good.
Yeah. Okay.
I have an exam day after.
So for example, with yourself, I'm assuming you have courses in kind of the two streams where you like some computer science courses, some neuroscience related courses, and then same with you give both.
Yeah.
What do you find is more challenging? Like, is it hard to constantly be switching, like even like your mindset between like maybe more like medical related courses as opposed to more like technical courses?
Honestly, for me, I love the change. When I need a break from business or economics, then I can go to psychology or computer science. So it works really well that way, and like I like variety. I get bored of the same thing. So for me, it's like a plus to have these two different things. What about you?
I would probably say the same thing, because in neuroscience, mostly like the courses are kind of memorization based, especially in the exams and stuff. Like, you have to like memorize a lot of stuff and recall. But for computer science, I find it more applied in a way that we have a lot of projects where we have to actually like write some code scripts. I think it's a good balance.
Yeah, I found that between like my own education, neuroscience and biology courses tend to be a little bit more on the memorization side. So a lot of flashcards, stuff like that, which is, I think that like there's a time and place for that. But then if you look at computer science or engineering and the courses I had to take when I was doing those degrees, it's a lot of kind of interactive problem solving and not so much memorization. And so it really kind of stresses various parts of the brain to be able to kind of switch between these two different kind of modalities of learning.
Yeah, that's so true, and it's so fascinating, neuroscience and AI, and how you have sort of combined the two in your career. And I guess for our audience who isn't completely familiar with this field, how would you define NeuroAI, and what exactly the most about this field?
So NeuroAI is kind of a unofficial term we use to describe our field. Some people call it, like more formally, computational neuroscience, but that wouldn't. There is kind of NeuroAI within that, because not all computational neuroscience involves artificial intelligence per se. But if you want to talk about the stream of NeuroAI, as the name suggests, it's an integration of neuroscience and artificial intelligence, and a lot of people in our field present this kind of feedback loop to kind of describe the things that we do, where on one hand we use artificial intelligence and machine learning to study the brain and cognition, but then we also use the brain and cognition as inspiration to build kind of next generation AI algorithms. And so there's this kind of interesting feedback loop. I would say though that if you are interested in this space, or if you're already in this space, you'll know that a lot of the research and development to date, and presumably even moving forward, is in one direction, where we're using artificial intelligence to study the brain. I think there's probably a lot of untapped potential for using the brain as inspiration to develop better machine learning algorithms. The field of AI originally started taking inspiration from the brain, Professor Jeffrey Hinton often talks about the brain being a big part of his motivation, and you look at other people like Alan Turing, he's a big inspiration of mine, and he was interested in these concepts of studying the mind in terms of computation. But kind of over the years, I think the field of AI and machine learning has kind of come out as its own and drifted away from neuroscience and brain science, where now if you go to a machine learning or AI conference, there may be no mention of the brain other than maybe the first 30 seconds of a talk, where they're like, oh, inspired by, and then the rest of it has nothing to do with the brain. And that's an interesting question that we talk about a lot in the field, is if we want to develop next generation advanced adaptive machines, do we need to study the brain? Is it possible that we can create intelligence on its own without actually looking at human intelligence? We don't know. I don't see it that way. I think that there's a lot we can learn from studying the brain and applying that to machines. But maybe it's not necessary. I don't know. What do you guys think?
I guess the entire reason I'm in cognitive science and computational stream is because I see that parallel too between the brain and AI and how machines are built in general, and it's so fascinating. And I thought that more people would talk about it, and I'm surprised that it's not that spoken about as much as I would think.
So can I ask you a question? So you bridge this between like business and economics. What would be an example of using like cognitive science in that domain? Like
in economics or
business? Or as economics or business. Like what is something that's, if you are a student, for example, coming out of, say, just cognitive science, what could your contribution be to the field of business? I know there's lots, but I'm just curious to know, like, what's your take?
So the way I think about it is like perhaps setting up a business or pursuing an entrepreneurial venture that kind of combines cognitive science with business. An example would just be something like Neuralink, working on creating brain chips and sort of BCIs that can further that technology. But on a day-to-day level, even I guess understanding the cognitive biases that exist and kind of applying that, so various marketing strategies or just dealing with different types of business people and founders and negotiating with them. I guess from that perspective, that's where the cognitive part comes in. And the computer science, machine learning, it's so prevalent, any sort of data analysis and any sort of insight generation, you have to go there. So I guess that's what I see, but I would love to hear your thoughts on it.
Yeah, I would agree with that. It's business is as much about the people that not only that you're serving, like the services that you're providing, but also the people that are providing them. So I think that a background or some type of knowledge in cognitive sciences could be beneficial not only for you as, say, a leader and your ability to work with and develop a really cooperative environment, a good environment for your staff, but then also has the potential to understand the psychology of your customers and maybe leveraging that to provide better services or products.
Yeah, I just finished a course in behavioral economics where, so the entire course was about finding these heuristics and cognitive biases in the field of economics and how they kind of apply to us. And we fall into so many things and so many of these techniques. It's crazy.
Yeah, I would say so. I feel like business is more like a people's game in a way, that you're dealing with almost managing a lot of relationships all at once and trying to kind of satisfy both ways, your suppliers as well as the people that you provide to. But yeah, that was a great chat. I think I'm just gonna shift the focus back on the machine learning. But yeah, so we do know that your work on integrating machine learning algorithms with the musculoskeletal models to study how the brain controls as well as how it optimizes motor control is quite groundbreaking. And could you please explain how these models kind of predict the motor control in humans?
Yeah, so I mentioned that in my at least my second master's, I was crazy enough to get 2 masters. Yeah, I don't know if I recommend it, but in hindsight, it was really beneficial, but at the time, it was quite stressful. But in my master's in engineering, and again, this is at the University of Waterloo in the mechanical department, we were trying to be able to understand how the brain controls the body. And maybe in your own courses, you may talk about this concept of like understanding. What does that mean, right? What does it mean to understand the brain? What does it mean to understand how the brain, say, controls movement, which we call motor control? So when we talk about understanding, those of us in the field, we often use this quote by Dr. Richard Feynman, who said, "That which I cannot create, I do not understand." And what that essentially means is that if one wants to understand something, truly understand something, a great way to do that is by building it or creating it. So if you want to understand an engine, for example, you can take it apart and put it back together. But for the brain, you can't necessarily do that. And so that's where computational approaches come in, where we can do a lot of things in simulation. And we're able to do this process of kind of reverse engineering and finding out how does the system actually work. And so in my master's, we did this for human motor control, and a lot of the work that we did is kind of inspired by evolutionary biology and this concept that humans move in ways that are perhaps some relation to an optimization. So if you look at something like evolutionary biology, we have shown that humans and animals move in a way as to, say, minimize energy expenditure. And this is important for survival because you don't maybe know where your next food is coming from, or if you have to escape a predator, for example. And so we wanted to apply these concepts of optimization and control theory to model and predict how humans move. For something like locomotion, it may be intuitive that, yeah, we may move if you're just walking. And again, from the evolutionary perspective, it may make sense that you kind of maybe the objective function for this optimization problem is maybe minimize energy. But what happens if you want to type on your laptop? What if you, you kind of bouncing your foot right now? What is your brain doing? Why is it doing that? Why is, if we were to assume it's an optimization and that you're solving or you're minimizing or you're maximizing some objective function, what is that? What is that cost term? And identifying what is this objective function or this cost function is a process known as kind of inverse optimization or inverse optimal control. This is perhaps one of the most elegant, fascinating questions that I've ever come across. This really, it didn't spark my interest in neuroscience and AI because that was earlier on, but this really accelerated. I became so fascinated with this idea that, and this is an abstraction, I'm not claiming the brain actually does this, but it's so fascinating to think that we can use math, we can write an equation that is able to accurately simulate how the brain controls, say, your hand. This is incredible. And so we started developing these models of, say, upper limb movements, and we were testing out different optimization objective functions, minimize accelerations, minimize joint angular velocity, all of these different things that one may think is important for a given task, and seeing the resulting predictions of these different objective functions, how do they compare to experimental data? And the cool thing is that when you use this kind of computational framework, it's fully predictive. We require absolutely no experiments. which is very different than my original background in kinesiology, where they do a lot of experiments. If you do an undergrad in neuroscience tends to be a lot of experimental work, a lot. There is an argument to be made that with computational approaches, and this is kind of the whole theory of computational neuroscience, by introducing computation and theory, we may be able to explain the underlying mechanisms that give rise to all of these experiments. So as opposed to doing like thousands of experiments, what if we know the underlying algorithm the brain is using? And if we can kind of reverse engineer and backtrack and find out what that is, we may be able to not necessarily get rid of all those experiments, but as opposed to just measuring the output behavior, we can understand what is actually happening in the brain. And so that was a big part of my work in motor control, and we're still doing that, where we're developing these mathematical models. That's using classical control theory. We've also started looking at things like reinforcement learning to be able to model human behavior, and that's also inspired by the brain. So there's a lot of evidence to suggest that reinforcement learning actually does take place in the brain. And reinforcement learning as a machine learning topic was originally inspired by the brain, and looking at dopamine reward-based systems and stuff like that, which is really important for things like cognitive science and understanding human behavior, maybe even from a business perspective, right? And so we've been using reinforcement learning in addition to classical control theory to be able to model how humans control their movement, and then comparing the output of those predictions to experimental results and seeing whether or not we're developing a relatively biofidelic model of what is happening in the brain. So that's a long-winded answer, but in sum, we are working in the space of computational motor control, and we're developing these models of the brain using things like classical control theory in addition to reinforcement learning.
That's very interesting, and so many insights about the brain. You mentioned that you can accurately kind of model the movements, and I'm wondering how accurate is that? Like, are there any kind of shortcomings, and what do those suggest about human movement or machine movement?
That's a really good question. And it's important to be upfront about, we've had some successes, but we have a long way to go. I in no way, shape, or form claim that our mathematics encompass all of adaptive motor control, right? Like we know so little about the brain and how it actually gives rise to complex behavior, right? Which is a really fascinating thing. How does neural activity in the brain give rise to intelligence? Like, I can do so many amazing things like dexterous manipulation. All of that comes from very simple computations that happen in the brain, or the spinal cord, depending on what we're doing. The unique thing about human motor control or animal motor control is that it's highly. If I'm walking or if I'm doing some movement, something happens, there's a perturbation, humans are very easily able to adapt. Yeah. Our mathematical models, whether it be using control theory or reinforcement learning, struggle with that type of adaptation. It doesn't have that kind of general adaptive intelligence. We develop models in simulation under very tight constraints. So, for example, some of the work in my master's, when we were trying to mathematically model human motor control of upper limb movements, it was very simple, planar 2D movements in a very confined space. Everything was very tightly controlled. It wasn't necessarily freely behaving individuals just kind of going about their everyday life. But there is work in that space. There are some really fascinating animal experiments being done right now in neuroscience where they're trying to be able to model this adaptive motor control of animals freely behaving in an environment like a mouse or something, just kind of going about their lives. My lab is nowhere close to those level of advances, but it's really inspiring to see the field trying to be able to tackle this issue of adaptability, right? So that's probably one of the biggest things, the differences between our models of human motor control and what we see in the real world is our models are simple mathematical abstractions of the real world. And in order to get them to work, we start off with really tight constraints. And as we get better, we can start relaxing those constraints. And hopefully over time, we can develop models that are more like the real world and are able to adapt to the various things that happen in the real world.
Yeah, thank you for your candidness. And I'm sure you have many successes headed your way.
We'll see.
Yeah.
I guess that discussion kind of sparked this one point around like human cognition having some sort of this capacity for a combinatorially like explosive number of tasks that it's capable of doing, but like really limited number of neurons that we have. And like to see that how it actually transferred the real world and into mathematical models is really interesting. And as Arnav said, I think we have a long way to go, but I'm hoping that we're gonna get there soon. But
yeah, we'll see. It's a really challenging problem, and that's what makes it so exciting.
Yeah.
That's one of the nice things about academia or research in general. It's a long-term investment. So one of the great things about academia, and especially for those of you, like those of professors who have like said like tenure, the purpose of tenure is it allows you to work on really challenging long-term projects without the stress of having to produce some immediate product or results. That's kind of one of the fundamental principles behind giving tenure to a professor, is that we're not going to put the pressure on you to generate some product in 1 or 2 years, but we want you to think really like how can we make fundamental advances in science and technology that may take decades, or you may never get there.
yeah.
And I think something like computational neuroscience and understanding human intelligence and artificial intelligence, this is something that's going to take quite some time. And I'm really grateful to have landed in the space that I am. And it seems like a really hard problem, but as a scientist, that makes it really fun.
Yeah.
Yeah,
The
really
more
fun.
challenging it is, the more fun it is.
Absolutely.
Yeah, exactly. So I guess like shifting gears a little bit from motor control into sensation, you also have some work in computer vision, right? And I was wondering, as someone with neuroscience background, how are you using your understanding of the human brain when designing models for visual perception?
So a lot of the work in machine learning and AI, I would say a lot of the advances that we're seeing came out of work that was, or most, came out of work that was applied to vision. Vision has for a long time been kind of the hallmark of a benchmark for our advances in developing models or machines that kind of recreate intelligence. This is one of the many reasons why like Dr. Hinton is so famous, is that they took inspiration from the brain in developing convolutional neural networks that have some really interesting properties that mimic and or are inspired by the brain, specifically the visual cortex and how it does things like hierarchical representation learning, which is a really fascinating concept actually. But even the computational units within a convolutional neural network are also biologically inspired. So if you've ever taken a course in computer vision, you most certainly probably have heard about Hugo and Weasel or some of the people that kind of inspired the field of computer vision, where they were doing basic science experiments in animals and able to show that there are neurons within our visual cortex, both humans and animals share these properties, where some neurons are attracted or respond best to edges, some neurons respond best to objects, and some neurons respond to specific orientations. And there is this hierarchical learning starting maybe from edges and simple features to shapes, and then shapes form faces, and then faces kind of lend itself to some type of interpretation. And they were able to kind of show this, and some of the basic computational units within a convolutional neural network, like the very concept of convolution or max pooling, these were actually directly inspired by some of this neuroscience research by Hugo and Wiesel, which ended up winning the Nobel Prize. And as the story goes, this research, which then gave rise to developing convolutional neural networks and deep learning, then just last year ended up having Geoffrey Hinton awarded the Nobel Prize as well. So that's interesting, where now we see these parallels between some really groundbreaking research, one directly inspired by the other, where we're looking at biological intelligence and then looking and developing artificial intelligence in the field of computer vision. We've done work in that space where we have also taken inspiration from biology and applied that to developing machines and artificial neural networks that are able to perform various visual recognition tasks. One of the defining features of the research that the computer vision research that my lab does is we really try to capture visual intelligence in the real world. And then what that requires is us to have data from real world environments. And so our lab is, I think, very well known for developing large scale data sets that are used to train our deep learning models. And we collected this data by having subjects walk in the real world wearing wearable cameras, whether that be using our custom smart glasses or other types of wearable systems, gathering these real world environments. Not only the noise of a real world environment, but the perspective. And we call that egocentric vision, where you're perceiving the world from a first person perspective. And that's what our brain does. Our brain receives that first person visual information from our eyes, and it uses that information for processing and understanding. So if we want to be able to develop artificial neural networks that can mimic the brain in some capacity, it makes sense to use that type of data diet, where we're taking in similar information to what our brain does. And so that's most certainly one way in which one of the things we're best known for in the computer vision space is developing these data sets that mimic the information that the brain would receive. And actually, a lot of that data was personally collected by myself, walking around the University of Toronto. So if you've ever actually gone into any of our data sets, and if you're a U of T student, you'll recognize a lot of the places. My students and I ended up getting maps of the University of Toronto, and each one of us would be responsible for kind of tackling various buildings or various parts of the campus on each day. And we did this for several months. And we were collecting just a lot of data, millions of images. You really get to appreciate the beauty of this campus when you've literally walked every corner of it, literally every corner. And there's a lot of really beautiful architecture around campus, and I really gained an appreciation for this. Yeah. So that's some of our work in computer vision. On the algorithmic side, we've developed things like convolutional neural networks, which again, as I previously mentioned, take inspiration from the visual information processing in the brain. But a big part of the information processing in our visual cortex also includes feedback connections, both local feedback connections as well as long-range feedback connections. And so we've also been working on developing recurrent neural networks to be able to simulate some of that feedback that one would get as we kind of go through and learn representations through the network. And then another way, this is probably the last example I'll give, is the human brain is very efficient. This may be a topic that you guys talk about in your courses. This comes up a lot in our work and in the conferences that we attend. And one could make the argument that if you're working in the area of, say, supervised learning, which is very common in the field of artificial intelligence, that is possibly not representative of what is happening in the real world. So I often think about my daughter when we're talking about these things. When I'm teaching my daughter about objects in scenes, I don't provide her millions of training images with semantic labels. I don't show her tens of thousands of images of a table like that, be like table, 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 table. I don't do that. But we do that with our machine learning models. And so we've been exploring using more biofidelic learning algorithms like semi-supervised learning, and now we're getting into the space of self-supervised learning. And presumably this is a little bit more aligned with how the brain learns to do visual recognition. So those are some of the ways that we've been kind of developing artificial neural networks that take inspiration from the brain and that are able to process visual information that somewhat also mimics that which the brain would receive.
Yeah, thank you so much for sharing.
We keep coming back to these parallels between the brain and these artificial networks, or AI in general, and there are so many of them. And I guess in a more sort of detailed and maybe general sense, in what ways are these artificial neural networks, you can speak about it, not just CNNs or RNNs, but perhaps generally, are they similar to the brain's mechanisms, workings, and how are they different?
It depends on the model you're talking about. For example, if you think about something like reinforcement learning is very much inspired by, as I previously mentioned, kind of dopamine reward-based learning in the brain. But there's a lot of things that there are reinforcement learning models in the AI space are very quite different, actually, from how we suspect humans acquire information and knowledge through interactions. Because at the end of the day, that's really the theory behind reinforcement learning, is that one can gain understanding and intelligence through interactions with an environment. But there seems to be some fundamental differences even in the output behavior. I previously mentioned this limitation of adaptability.
Yeah.
Our reinforcement learning algorithms are not as adaptive as whatever computations are happening in our brain. They're also much more data and energy inefficient. So if you haven't seen this movie yet, I would really encourage you to. It's a documentary on AlphaGo. I'm not sure if you've seen it. I would highly recommend you watch it. It's on Netflix. And it goes to, you're familiar with AlphaGo?
Yeah, that game that beat a human, right?
Yeah, in the game of Go.
Yeah, in the game Go, yeah.
And it's an amazing documentary, first of all. I'm a big fan of Google DeepMind. And I would definitely encourage you to watch it. And it's really interesting. They go through and they show you how, and for maybe your listeners who aren't aware of this, Google DeepMind, which is an AI kind of powerhouse now, they are working in the space of developing general artificial intelligence. And in the process, in the pursuit of that goal, they've been having little benchmark competitions to see how well they're doing compared to even, say, human intelligence. And a lot of people in our field made the argument that the game of Go is something that may not necessarily be achievable or to the level of the level which a human can play using a machine learning algorithm. And so they took on this challenge and they were able to develop a reinforcement learning algorithm, a relatively simple one actually, that using kind of large scale data was able to outperform quite literally the top Go player in the world.
Yeah.
And it was really a breakthrough for artificial intelligence. One thing they don't mention in the movie, and one thing that we often talk about in the field of NeuroAI and computational neuroscience, is that their algorithm was incredibly energy inefficient.
Oh.
Is like orders of magnitude. So the human brain requires approximately 20 watts to do the computations in everyday life. I think their algorithm was like 10,000 watts or something like this, if I recall correctly. So orders of magnitude more energy inefficient. That's a big way in which our machine learning algorithms significantly differ than the human brain, is this notion of energy inefficiency. That being said, there is a branch of research in computational neuroscience looking to tackle this. So you may or may not be familiar with the notion of neuromorphic computing and developing hardware that is kind of leveraging some of the principles that we see in the brain in order to develop more energy efficient hardware. This is something that's presumably is going to be, or at least I think so, more and more applicable in industry as we look to transition AI from these large data centers to mobile phones or laptops or smartwatches. So I think this concept of neuromorphic computing, and as we bring AI into the real world, will become more and more applicable, because we need algorithms that are not only very accurate, we need algorithms that are efficient enough to work on wearables, essentially. So that's one way in which the brain and our AI algorithms differ. Yeah, I would say that's one of them.
Yeah, wow, efficiency. I haven't thought of it until now, honestly.
Yeah. Because usually, like, when topics around AI comes up, like, the most, I guess, the benchmarks are kind of focused around the accuracy of the models, but the efficiency bit, as you mentioned, like, even in the documentary and stuff, it's almost, like, sidestepped, right? Yeah.
Yeah, like, it may or may not be important. But there's people working on neuromorphic computing chips, which I said are inspired by some of the hardware in the brain. But they're also working on the algorithmic side, developing things like spiking neural networks, which are certainly more biofidelic and take more direct inspiration from the brain, because that's presumably the computing units within our brain are the firing statistics of spikes. Presumably that's how neurons in the brain communicate and give rise to intelligence. How they do that, we're still trying to figure that out. That's a very hard problem.
Yeah.
But you mentioned like companies like Neuralink. That's one way in which they're able to interface with the computers and phones and all these other things that they're working on, is that they leverage our knowledge of spikes and the statistics of spikes and decoding these statistics to be able to infer intent. So we know that spikes appear to be relatively important for information communication and processing in the brain. Maybe we should develop artificial neural networks that also leverage spike communication. And so that's kind of the whole purpose of spiking neural networks, which, going back to your original point, are very energy efficient. They're very efficient. Perhaps one of the reasons why it's not as well known is that we're still working on trying to develop them and to be able to use them in a way that kind of rivals that of, say, convolutional neural networks or recurrent neural networks. So they hold a lot of potential and promise, but we're still, it's a work in progress.
I feel like at this stage it almost sounds like a trade-off, right? Like between choosing which one to go with.
Yeah.
Yeah, I see.
Have either of you learned about spiking neural networks or different type of neural network architectures?
No.
Nothing spiking neural networks, but like, I mean, not really an expert, but of course, like CNNs, RNNs.
So in your neuroscience courses, have you guys talked about like spike rates and how the brain communicates information and synapses? And
Yeah, and even the part around, I remember this like quite like vividly. Based on the audio like frequency that you're hearing, it actually transfers in terms of the waves that you're seeing from the brain as well. Like in neuroimaging, the brain waves tend to match the frequency of the sounds that you're listening to at the point. Yeah, so it's quite an interesting point. Yeah. Well, I guess the part around Neuralink is a great segue to the next part of the discussion, which is going to be on brain-machine interfaces. So I was just wondering, how do we integrate artificial intelligence into BCI systems, and in your own perspective, how close do you think we are to kind of having seamless neural interfaces that can adapt in real time to human intent?
So it's probably worth just taking a second to explain what is a brain-machine interface. So the idea is that intent originates in the brain somewhere, and that this intent can be associated with some electrical activity in the brain, which can be recorded using various types of sensors. These can be recorded using things like neuroimaging. You can use fMRI machines or other machines that are as portable, or we can use electrophysiology like EEG sensors or intracranial sensors, which is what they're using in Neuralink, where you're not necessarily recording on kind of a more coarse scale, but you're recording the spiking rates of individual neurons, and you can record up to like 1,000 individual neurons. And so one of the real breakthroughs in Neuralink is that it allows for, they've essentially created a device, a microarray that is able to be implanted into the motor cortex, for example, and they're able to record from so many channels simultaneously. That's really one of the main innovations of Neuralink, is the development of the hardware. Okay, so once we have this information of the neural activity in the brain, if we were to ask somebody to do something, whether that be like wanting to move a computer cursor, for example, we can associate, as the user is like using the device and training and learning the system, we can associate their intent to want to move a computer cursor, say to the right, and correlate that output behavior with some neural activity in the brain, and you're developing these mappings. And at a very high level basic concept, that's what a brain-machine interface is you're recording neural activity in the brain, you're developing a map to then some output behavior. So you can go from neural data to behavioral data, and that behavioral data could be interacting and controlling a computer cursor. It could be controlling your phone, maybe a robotic arm if you want to use it to take a drink or something like this. The fundamental technology that makes this possible, yes, there's obviously advances on the hardware side and developing systems that actually collect the neural data, and that's a big part of Neuralink. But what do you do with that data once you have it? How do you decode that information into something that can be delivered in an actionable way? That's where machine learning comes in. That's where computational neuroscientists come in, like myself. We take the data and we process this information to be able to decode what does the user want to do. Okay, this is challenging. Also depending on the sensor modality that you're using. But that is one of the ways in which machine learning is being used to decode these neural signals to go from the neural activity recorded in the brain to some output behavior. Okay. Now, we're working on decoding that information, where you're going from neural data to behavioral data. But there's also the opportunity to encode information, where you're going from behavioral data back to neural data. And I'll give you one example. We're now looking into this space where if somebody were to sit in an fMRI machine and they were to do some task, it could be a speaking task, it could be a motor control task, like maybe playing with the digits, or even some cognitive tasks, like playing a game. We know their output behavior that they're doing, and we're getting neural recordings at the same time. Okay? So we can develop mappings to go from some output behavior and be able to kind of infer what is the neural activity in the brain. So now, say you were to turn off the fMRI machine and you had the user do the same task. We could then create models to predict what the fMRI machine would look like. I never said accurately. We're working to develop models to accurately do this. So somebody, say, is playing a board game, or let's do speech, for example, because we haven't really talked a lot about speech today. Somebody is doing some speech, some dialogue, and we're recording in the fMRI machine. We can then turn it off, and as they're speaking, we can then use that same model that we used to create that mapping to then infer what would the fMRI scan look like. You can then, that's encoding. You can then do the opposite, where now just based on the neural activity in the brain, we can then predict what are they actually trying to do? What are they doing? And this is decoding, where you're recording from the brain and then trying to infer what are they wanting to do. And this is really interesting for applications for, say, assisting patients with various motor impairments like ALS or spinal cord injury, where the neural activity, the intent to speak, the intent to do some cognitive task or motor task is still there, it's still intact. It's a communication problem. It's not resulting in output behavior. So if we can decode what is their original intent, we can then presumably then use this mapping model to then be able to control whatever they were planning on doing.
That's quite impressive. And again, I think this also refers back to our point around reverse engineering, right? Like going back and forth between encoding as well as decoding.
Yes, to a point. We talked a lot today about models and machine learning and computer algorithms and stuff like this. There are fundamentally two branches of models we're developing. One are encoding, decoding models, where we're just trying to understand what is the inputs and outputs of the system. When you're developing a machine learning, if you're developing a neural decoding algorithm, for example, we take neural data recorded in the brain, we develop a machine learning model to then map that to some output behavior. And our models, even the ones that we're developing right now in my lab, can do this with fairly high accuracy for very basic motor control tasks. That doesn't necessarily tell me, though, what are the internal workings of the brain. It just tells me, for this pattern of activity, what is the expected output associated with that neural activity. It doesn't really tell me what is happening. It doesn't provide a mechanistic understanding. That's some of the other research that we're doing, which I was talking about before, where we're trying to develop models to not only characterize, for example, how do we do visual recognition, but how do the internal workings of the model, how do those compare to the internal workings in the brain? We want to know step by step, are we developing models that capture the say, the computing elements as you're doing some task that we also see in the brain. And so those are kind of like the two branches that our lab and most labs in the field are working on, where you're developing either system level models that are kind of fall under this branch of encoding, decoding, where you're not really caring about the internal workings of the model. You just want to be able to develop a model to go from input to output. Or you develop a mechanistic model where you're trying to understand what are the actual computing elements in a model, and whether or not those internal elements, those internal representations that you're computing, if those give us a better understanding as to what is happening actually in the brain. And so they're kind of like two different branches of models with two different objectives, actually.
Yeah, so it sounds like the inner workings of the brain are kind of like a black box, and you're trying to kind of understand what's happening within. Is that similar to explainable AI?
Exactly.
Yeah.
So, as neuroscientists, we actually, and I'm talking about you as well, as neuroscientists, maybe not you, but we can really contribute to the field of AI because we have the potential to develop tools that, like, for example, developing artificial neural networks that are not black boxes, but we can treat them as experiments where we can see how do the inner workings of a neural network compare to the inner workings of the human brain, and be able to associate some biological concepts to them. So not only are we developing models like artificial neural networks that are more explainable and interpretable, we do so in the context of the human brain. So developing mechanistic models of the brain very much coincides with this concept of explainable and interpretable AI, where we don't treat them as black boxes. And they're not black boxes. We can now start to study what do the internal representations mean.
Have you learned anything out of the ordinary about human cognition by creating these computer models that mimic human cognition?
I think in my lab particularly, we've been working on breaking down this problem of cognition into actionable projects. Cognition is very complicated. It is also a high-level term used to describe a number of different things. One of which is perception. And I think that we've gained insight into human visual perception by developing these models, for sure. I would say probably some of the best insights that we've gained about cognition have come from motor control. This is obviously a big part of my research because it applies not only to understanding the brain, but also to the development of brain-machine interfaces. And I find that our research in inverse reinforcement learning and computing these underlying objective functions has been one of probably the most interesting things. And that's probably one of the, at least for me, one of the most fascinating aspects of developing artificial intelligence, and how through that development we've gained further insight into some of the fundamental principles that govern the brain, the underlying mechanisms of the brain.
Thank you for sharing that.
Right, I think this is one of my favorite questions that we're going to be asking you today.
Okay.
So there's a growing conversation around using NeuroAI not just to restore the lost function in humans, but also to kind of like use it to enhance some human capabilities. And I was just like wondering, where do you stand in this line between therapeutic purposes and enhancement?
Are you referring to AI or brain-machine interfaces?
I think we can go with whatever you want to interpret it as. Because the applications of AI for brain-machine interfaces are so relevant, right?
Well, one could make the argument that AI is already extending our cognitive abilities. Do you use ChatGPT?
A lot.
Not a lot. Yeah.
I use it all the time.
Yeah.
I find it's great for brainstorming.
Yeah.
There's still a lot of things it gets wrong. And anyone who uses these types of generative models, I'm using ChatGPT as just an example. There's a lot of different large language models out there.
Yeah.
But let's just use it as an example because it's arguably one of the more famous to the general public, at least. I would say these are AI technologies and they are being used quite broadly. And I would say, even through my own experience, that they are in many capacities enhancing our cognitive abilities. And I suspect that AI and machine learning will only have continue to have even a greater, broader impact in our society. So, yes, if we're just talking about AI, I would make the argument that it already is being used for enhancement, as you say. Most people, when they ask me that question, they're referring to brain-machine interfaces, though. I think we need to be a little bit careful about hyperbole. There is a large gap between what top neuroscientists have accomplished and what industry leaders claim these things can do. There's quite a big gap there. Yeah. I'm always a little bit skeptical when I hear people in industry talk about brain-machine interfaces and how it will do all these amazing things. It has the potential to one day do that. It does. How far we are away from that, it's hard to predict. It's really important, though, to emphasize. Right now, we're using, for example, implanted brain-machine interfaces to be able to restore function to patients who are quote-unquote severely disabled. Okay? These are individuals that have, for example, ALS or spinal cord injury. I say severely disabled in quotes because I personally think that's a little bit of there's a negative connotation associated with that type of language. And we don't usually use that in my lab. And we are able to provide some assistance to patients. And while that can have really meaningful implications for their quality of life, it's important to acknowledge that even some of the greatest advances in the field are far from fully restoring motor function or the ability to speak and communicate. There's amazing research being done all around the world in brain-machine interfaces. All around the world. Even our most advanced systems, I would argue for something like speech, are nowhere close to the level of, say, bits per second which we're communicating. Yeah. Maybe because I talk really slow, but there's a lot of potential there, and there's brilliant people working on this problem. It's just a really hard problem. So while we can provide some level of independence and autonomy to people who we feel the benefits outweigh the risks. So if you're thinking about something like an invasive surgery, putting electrodes in someone's brain, there is obviously risk associated with that. And so when you're getting things like FDA approval or running clinical trials, we start off in cases where we feel that the benefits significantly outweigh the risk, right? And so we're starting off providing very basic motor and speech neuroprostheses for people who have these types of physical disabilities. And to the patients, in many cases, they're quite satisfied with what they're able to regain. They're not fully regaining motor function or the ability to speak, but even the littlest bit could have profound impact on one's quality of life, right? Imagine you couldn't speak at all. You couldn't tell your loved ones that you love them, or be able to, like, even just convey that you wanted to have your face scratched, maybe you're itched, there's an itch or something. So little things like that, just little things, can have a pretty big impact on one's quality of life. But to conclude, we need to be very careful about suggesting that we can develop superhumans that can interface with everything and have these superhuman capabilities. We're just able to manage having someone control a mouse on a computer. And that may seem silly, but that's really smart people working on the problem. Yeah. And that's the level in which we can provide to these patients. Not diminishing that. These are amazing accomplishments by the neuroscientists and neural engineers, and not diminishing the impact that can have on the patients. They may think that, wow, like this really helps improve my quality of life. But I think we are a long way off from like full restoration, and even further off from going beyond that to superhuman capabilities. But I believe in my lifetime, this is going to be more and more attainable. And I'm really excited to see what this kind of transitions to over the next 5, 10, 20 years.
Oh yeah, it's really an amazing journey, and the fact that you mentioned how big of an impact it actually is for like a patient's life, even though maybe like it's just a stepping stone in scientific knowledge, it's just super amazing to me. So thank you for sharing that. I guess to close it off, we really want to talk about beyond your work as a research scientist. I mean, it's kind of related, but it really stood out to us that you're the co-founder as well as the director for a summer research program for student refugees from Ukraine here at the University of Toronto. Could you share a little bit about your inspiration behind this program and maybe a student story that comes to mind?
Yeah, so we developed this program with the generous support of the Department of Computer Science and also the Vector Institute for AI. And it is only through that generous support that this program is possible. When the full-scale invasion happened, and it's important for people to say that because that's not when the invasion actually started. Russia began its aggression on Ukraine, one can say, starting in 2014. But when the full-scale invasion happened, it really moved me personally as a Ukrainian Canadian. Because had my family not come to Canada, I would be one of them. I would be one of these students. And I would hope that if I were in that situation, someone like myself and many others would lend a helping hand. And so we put together this program that was able to bring over students opportunity to continue their research and education despite the invasion. And in total, over the course of 2 years, we flew over around 60 students. It has had a profound impact on my life. It's really, obviously, I'm really flattered when they thank me and people appreciate the program and what it presumably I like to hope that the program had a positive impact on them. But working with these students has been probably one of the most gratifying things I've ever done in my life. I have not only helped create and manage this program, but a number of these students and other students that were not necessarily even a part of this program, who are Ukrainian, worked in my research lab, and I supervised their master's and undergrad theses. And one of the most important lessons that they taught me is, like, don't complain. They have every right to complain. They have every right to be down and to just want to give up. And every single day I'm inspired by their commitment and their strength, the willingness to be able to learn and want to continue to learn despite unimaginable stress, right? Like, we complain that, like, oh, I gotta go to class or something like this. They wish they had those problems. And so it really helps put things into perspective when you're working with students like that. One of the most surreal moments was when I was on a Zoom call with a student of mine, and the internet was cutting out and the electricity. And that was because there was bombs outside. This is a student, probably the same age as you guys. They're not a soldier, literally in their home office, just wanting to learn, do schoolwork. And that, I'll never forget that Zoom call, where they first apologized and said, oh, I'm sorry, it's the missiles outside. And it's such, it really puts things into perspective. And so I am so grateful for the opportunity to work with these students who show us such courage and commitment to education and learning. They actively seek out my lab and our program and want to learn. They want to, that is their passion. Like, I can't even believe that that's what you're concerned with. It's really inspiring. So whenever I feel tempted to complain or I feel overwhelmed, I always think about my students back in Ukraine. I have students I work with remotely that are there, and I have students that are physically here in Toronto. And I always think about them. And I may be their professor, but they're the ones teaching me.
I'm not even sure how to continue, but thank you so much for sharing. And I think there's a great lesson for humanity in that story that you kind of bring to us. So thank you.
Well, yeah, science kind of unites us all, and despite this war and the incredible horrors that go along with that, and first of all, other wars in this world, I have this personal relationship with these students and being Ukrainian, but that is not to say that this is the reality for many other students. And I'm just really grateful to have played a very small role in helping some individuals who had nothing to do with anything, that were just being unjustly attacked. And it is science and learning that united all of us, right? And so that's one of the amazing things about education, is it can bring people together.
Yeah, that's incredibly inspiring. Thank you so much for making the impact in their lives, and we should be grateful for what we have here, and we have a lot to learn from them.
I think so.
Yeah. I guess we can close off with, what advice would you give to young neuroscientists, engineers, business students interested in working in computational neuroscience or NeuroAI, and any emerging areas of skills that you'd suggest they should focus on?
I think I would kind of close with going back to what we started with, was we began our conversation talking about my background. And I really do value multidisciplinary education because that is my background. I have a very unconventional background. I'm not aware of many people that have degrees in neuroscience as well as mechanical engineering, and it's not very common. But in hindsight, it was the best thing that ever happened to me. But at the time, it was really hard, actually. It was really hard to jump from a field to another field. And so I would recommend students, as you're going through your education, whether that be starting in high school all the way through maybe undergrad or graduate school, consider taking a multidisciplinary approach to whatever problem you're looking to solve. I think there's a lot that can be gained from diverse perspectives and schools of thought. I'm a big proponent of diversity. Unfortunately, in some areas it's being attacked, and I think it's quite ridiculous, because I think that there is nothing that drives innovation forward better than diversity, actually. And so I would recommend for students to do kind of what you guys are doing. Both of you, from what you've told, is that you both have education and training right now in two different disciplines. And I think it is by, like if we're going to talk in our field, I would encourage neuroscience students to take courses in computer science. And I would encourage people in computer science to take courses in neuroscience and cognitive science. And I think it is through this kind of multidisciplinary approach where you can gain an appreciation for different schools of thought and different perspectives, and it kind of enhances your ability to tackle a problem even more independently. And this is for my students who maybe want to go into a startup culture. In a startup, you don't necessarily have the resources and means to have a specialist in every single area. So if you are interested in entrepreneurship or getting involved in a startup, it can really benefit to have individuals who each have the ability to work kind of independently and autonomously and have more of a broad, widespread background where they're kind of a jack of all trades, master of nothing. So I encourage my students to do that, wherever possible. If you're a neuroscience student, go outside your comfort zone and try to learn computer science, machine learning. And if you're a computer science student, go outside your comfort zone and learn about cognitive sciences and neuroscience. And I think that makes for a better, more well-rounded person.
I couldn't agree more. Thank you so much for being here. We truly, truly appreciate it. Thank you so much.
Thank you.
Thank you so much for your time. It's been really insightful conversation for the both of us, and I think everyone in this room.
Thank you.
Hoping for our listeners as well. Thank you.
Thank you.
That's a wrap for this episode of NeurOn Air. We hope that you enjoyed this conversation and left with some electrifying insights. If you liked what you heard, subscribe to stay updated on future episodes, and don't forget to follow Neurotech U of T on social media for more cutting-edge content. If you have questions or topics you'd love us to explore, feel free to reach out. We'd love to hear from you. Until next time, stay neurocurious and keep pushing the boundaries of neurotech with us. This is NeurOn Air, signing off.